Hello, welcome to Chapter 9, Section 4, where we're going to introduce the idea of transforming quadratic functions. In this section, we're going to start to talk about taking the parent function, which is this one right here, just f of x equals x squared. This is the simplest that a quadratic function can be. You're not multiplying the x squared by any number other than 1, which doesn't change it. And you're not adding anything to it. I know in the last couple sections we talked about ax squared plus bx plus c. In this case, the a equals 1, so you just get x squared, and the b and the c equals 0. This function, we call it the parent function because everything else comes from that. Every other quadratic function is a transformation of that. And we actually explore transformations a lot in Algebra 2. That's why I kind of called this introducing transformations, because we're going to be seeing it a lot more. I didn't reprint it. I am kind of bugged by the fact that there's a gap here. I must have tabbed over without knowing it before I printed it, but sometimes we just let things slide. Okay, so here's what you need to know. What happens if you change the a? So again, this is the parent function where a equals 1. We say y equals a times x squared. And in this case, the a equals 1. You're just multiplying by 1. That's the hidden 1 that I've been talking about so much throughout the year. So we're going to explore what happens if the a is something other than 1. What happens if the a is bigger than 1? What happens if the a is less than 1? And what happens if a equals 0? And what happens if a is negative? So there's a lot of things we're going to explore. And it's kind of summarized here for you. When I take a picture of this later, the slides that you can look through, take a look at this and kind of go over it a little bit. But let me pull out Desmos here. I'm borrowing my wife's iPad, her personal iPad actually, because I'm recording with my iPad. So hopefully you can see this. And I'm showing Desmos. Let me get rid of that reflection. All right. So here's my function y equals a to the x power. You can see it right here. It's in red. You look right here where it shows it in red. I've got some other functions that I've already put in there that I'm going to be using in just a moment. Okay. What Desmos does is it allows me, when you give it a letter, it says, if this is not a letter that I recognize, usually we use X and usually we use Y, and Desmos is programmed to recognize those as the independent and dependent variables respectively. But if you type a letter that it doesn't know, it says, oh, that must be what we call a parameter. And do you want us to have a slider for that? What a slider is it allows me to slide this little thing right here. This is a slider. Slider is not a math term, it's a Desmos term. This slider right here allows me to change that a from anything from -10 to +10, and I can actually tap on those numbers and change those numbers too. That's not important. I'm just going to go between -10 and +10 for now. Currently, and this is the default, currently a is set up as 1. So this graph right now is just 1 times x squared, which is the parent function that I just had. So let's think about 3 things. What happens if I make a bigger than 1? All right, and actually, you know what I'm going to do? I'm going to do this real quick. I'm going to put y equals x to the second power, and let me change the color of that. I'll change that to, let's say, purple. I like purple. What the heck? Now you can see it's purple, but the purple is right on top of the red. If I tap on the red one, now it moves the red to the front. Okay, and that's what I'm going to have. The purple one is still in there. I'm going to change a by hitting the slider, or moving it actually, and then that's going to change the red graph. So if I move this over closer to 10, let's say 4.2, look what happened to the red graph. The purple graph is still y equals 1 times x squared. That's where I started. But now with a being bigger than 1, greater than 1 I should say, that graph got skinnier. It moved up like that. And if I move it all the way to 10, it's going to look very skinny. And if I picked a way bigger number than 10, then it would even get more, we call it narrow, more narrower than it is. So it seems like what happens is, as the A gets bigger, I end up squeezing my graph, squeezing it this way. But that's not really what's happening. This is actually kind of hard to see. What I'm actually doing, I'll zoom out a little bit, is that I'm pulling it, like I grab it and I pull it up that way. So I'm pushing everything that way. This is called a vertical stretch, and you'll learn about that in Algebra 2. This is called a vertical stretch. With quadratics, vertical stretches kind of look like what we also call horizontal compressions. You don't need to know that for this section. Sorry, I got the hiccups. But we have to, how do we know the difference? Based upon what we see in the function. Okay, so, and if I zoomed way far out, now I'm up to like y equals 100. This point right here, if it lets me, I don't think it'll let me, but this point right here is 10 100s, because 10 squared equals 100. But this one is actually, should be something closer to, I don't know, probably 2 100. Okay, so we got that part. Let me go back to this. So if the A is bigger than 1, then it makes the graph more narrow. What happens if A is less than 1? Now, if I get it back to 1, I always have a hard time with that. Ah, so close. I know I can tap. Oh, see, I always have a hard time with that. Come on. There, I got it. If we put it back to A equals 1, now my graph that I'm changing has now matched up with my parent function. But now watch what happens when I make it less than 1. And I got to be careful because the negative is going to do something different. I'll try to show you that. All right, so I'm going to move this way. Whoops, see, I went to negative. Got too close. There, that's good enough. So now look what happened. This is called a vertical compression. I'm squeezing it down, although it's really hard to see. What you can also look at is that from the purple, I've pulled it away from the purple graph, I pulled it away to make the red graph. And if I'm real careful, I might be able to make it a little bit wider. And of course don't want that one yet. There's 0. I should probably talk about 0 while I've got it. So anyway, this is really hard to do with Desmos with the touchpad. I do a lot better with my laptop. I think I can actually type that in. I'll show you what it looks like. Okay, so now I'm at 0.1 and I'm making it pretty wide. And if I do 0.001, that looks pretty flat. It's not. See how it curves up? But it really looks pretty flat. And I had this just a moment ago, but now I'll show you what it looks like. If it's 0, that means you're multiplying x squared by 0. This is a horizontal line. That's why we don't let a equal 0, because then it's no longer a quadratic. You've multiplied x squared by 0, and you need that x squared. You don't want it to go away. Okay, so 3 things so far, real quick. Well, actually 4 things, I should say, because we've got to talk about if a equals 1, then it's just nothing changes. It's just the original parent function. If a is bigger than 1, then it makes it skinny. And if a is less than 1, I'll try to get it right there. If a is less than 1, but still positive, remember that, but still positive, I end up with a wide graph. And of course, one more thing, if a equals 0, I don't have a quadratic at all. All right, so that leaves the last thing to talk about. What happens if a is negative? So there's 2 things that are happening. You've got the negative, which you can see flips it upside down, and you've got the 0.8 for this case, which makes it wide. And I'll put 0.1 in there so you can see what I'm talking about. Okay, so if I look at these 2 graphs, this one is flipped upside down from where it was, but you can tell that this is way wider than that one. Well, how do I account for that? And also, if I move this to like a negative number like this, then how do I account for that, whether it's wide or skinny? So there's two things that are happening. The negative flips it upside down, and the number that you're multiplying it by without the negative, like the 3.7. This is negative 3.7, but if I break that into the negative part and the 3.7 part, the 3.7 is bigger than 1, which makes it skinny. Yeah, so, and if I really push it all the way down to negative 10, then you can tell that that red graph is more narrow than this graph. So how does that affect it? How do we do anything with that if we don't have Desmos? Okay, so let's do a couple of examples. All we want to do is we want to put these graphs in order from the narrowest graph, that's the skinniest one, to the widest graph. So I look at the number that's being multiplied by the x squared. For right here, a equals 4. For right here, a equals 1/3. For right here, a equals negative 2. But I have to pay attention to the fact that I want all of them to be kind of oriented the same way. So I just want to know, I don't care whether it's flipped up or down for this problem. It didn't ask me that. I know this one's upside down. That's a frowny face. All the other ones are going to be smiley faces. All I need to do is check to see how wide they are. So then I do this. I do absolute value, which then that gives me positive 2. Of course, the absolute value every time, if it's a positive, just gives me the positive. But if it's negative, it changes it to positive. Okay, now I can put them in order. It's from the narrowest graph, the skinniest graph, to the widest graph. That means I'm going to pick which of these has the biggest a value, which is the positive part of the a value. That's going to be this one. So the narrowest, which I think is a real difficult word, I just say skinniest, it's fine, is going to be h of x equals 4x squared. The next, or since there's 3 of them, I guess the one in the middle would be this one. So that would be f of x equals negative 2x squared. And then the widest graph, the one that's going to be spread out the more, is going to be this one with the number that's less than 1. So that's g of x equals 1/3 x squared. Now I'm going to go back to Desmos, if I can pull it over here. I got it plugged in because my wife didn't charge it overnight. I'm at 4%, so hopefully we can make it. I only need it for this one. So I'm going to hide these graphs real quick so you don't see them. Let's go back to this. And here's the 3 graphs we just talked about. So here's y equals 1/3 x squared. It's hard to tell. In order for us to use words like narrowest and widest, we have to like compare them to other graphs. So here's y equals 4x squared, excuse me. And here's, oh, I forgot it right here. Y equals negative 2x squared. Okay, so from here it's a little hard to see, but it does look like the black graph, the graph that I used black for, is 4x squared. I'll move this over a little bit. That's what I said would be the skinniest one. The next one seems to be the green, which is negative 2x squared, which is what we said. And then the widest one, the purple graph, is the 1/3 x squared. So but it's hard to see because that negative 2x squared is upside down. So all I gotta do is I just go into it and change it to positive 2x squared. All right, which doesn't mean that you can just change every function. I'm just using that as the absolute value to find out what the number is, irregardless or regardless. I gotta look up which one works for that, whether you want it to be upside down or not. Okay, so again, the skinniest graph I see is the black graph. That's the 4x squared. Then the green graph, which is 2x squared, and then the purple graph, which is 1/3 x squared. Now notice I didn't set this up to do any other functions, so we're going to do the rest of them just by looking at the equations, looking at the expressions. So in this example, I've only got 2. So for this one, my a, or absolute value of a, equals 2. And for this one, my a is going to be negative 2, so the absolute value of a is the absolute value of negative 2, which also equals 2. So these two graphs are the same, just the only difference is that one is flipped vertically from that one, but they are exactly the same width, W-I-T-H. We'll do a couple more here real quick before we wrap this up. So first function, f of x equals negative x squared. My a is going to be negative 1, the hidden negative 1. So the absolute value of a is going to be the absolute value of negative 1, which equals positive 1. So that's the same as the parent function, just flipped upside down like a frowny face. For g of x, the a is 2/3. And of course, I want the absolute value of that, so I can go ahead and write it, but I'm just going to end up with the same thing. The absolute value of a is just going to be 2/3. So which one of these is the biggest number? Since 1 is bigger than 2/3, I gotta double check the question. Yes, I had to double check whether it was narrow to wide or wide to narrow. The narrowest, the skinniest, is going to be f of x equals negative x squared. Between these two graphs, the widest graph is going to be the other one, g of x equals 2/3 x squared. And finally, we'll wrap it up with this one. In this case, the a equals negative 4, so the absolute value of a is the absolute value of negative 4, which equals positive 4. For g of x, the a equals 6, so the absolute value of a equals the absolute value of 6, which is just 6. And for the last one, the a, what you multiply by the x squared, equals 0.2. So when I take the absolute value of that, again, it's positive, so it doesn't change. I just get 0.2. So which of these numbers is the biggest, making the graph the skinniest? That one. So the narrowest graph is going to be g of x, which equals 6x squared. The next biggest number is this one, so that means the next narrowest, or since there's only 3 of them, it's the one between the other two, the one that's not the extreme, just it's not too narrow, it's not too wide, it's just right, Goldilocks. This is going to be f of x, which is negative 4x squared. And the widest, the one that's going to be spread out further horizontally this way, is going to be this one, h of x equals 0.2x squared. Okay, one thing you can do to check your work, like from all of these, you can just switch over to Desmos, type them in, and like I showed you a moment ago, you can then see which one is narrow and which one is wide. So you can always use Desmos to check your work. All right, we'll see you in the next video.